The purpose of this video is to demonstrate the use of a spreadsheet for taking existing inventory data or data from a pilot study and determining required sample sizes for each of several candidate pre-strata for the full inventory. The first thing I have here is this example tab, which just sort of gives a general conceptual overview with a simple example of what happens later in the spreadsheet. So in this example, we have 10 plots, maybe from a pre-inventory or existing data. Each plot belongs to one of two strata. So you see in this example we have 5 plots in stratum 1, 5 plots in stratum 2, and I have 2 attributes. For simplicity, I just made it proportion forest and proportion non-forest, measured on each plot. You see in this example they're mutually exclusive. I just did it for simplicity's sake, but it could have been volume per acre and trees per acre. The same principles and equations apply here. So the first thing we do is, from this raw data, we calculate the stratum level summaries. So for stratum 1, I've calculated the standard deviation of the sample of stratum 1, of the plots in stratum 1, for each attribute. So this is for forest, this is for the non-forest, the means using the same principle, and this coefficient of variation, which is just the standard deviation divided by the mean. I've done this for each of the 2 strata. I've highlighted in yellow the information which would be put into these spreadsheets that I will show in a moment, or the sheets I will show in a moment. The other information you need to proceed is the stratum areas. In this example, we've got a map with 2 strata in a GIS, and we assigned each of these plots in a GIS the stratum identity. It's either in stratum 1 or stratum 2. You can only have 1 stratum per plot in this example. We need to know the stratum areas of those 2 strata from the attribute table of the GIS. So if we have a raster map, you can open up the attribute table, or you can calculate the areas of each polygon if it's a polygon coverage. And stratum weights need to be calculated. And you could do this in the spreadsheets later, or what I've done here is just pre-calculate them, given that the stratum weight is just the area of each stratum divided by the total area of the population. So in this example, our population is 10,000 acres, let's say. 3,000 divided by 10,000 is 0.3, etc. for the same principle for the second strata. So with this information that I've highlighted here, we can go to a more advanced example in the use of the spreadsheet for the actual assignment of the plots to the strata. So we had a certain number of plots from which we calculated these summary statistics. So these statistics are kind of like the analog of this information, just in a slightly different format. And in this example, we're only talking about 1 attribute. And this is the limiting attribute. And by limiting attribute, what I mean is, let's say we had 5 attributes that we're interested in, and we need to have acceptable precision for all 5 of these attributes. What you need to do then is choose the largest CV with which to proceed with the plot assignments, because if you use a smaller CV, a smaller assumed variability of the suite of attributes, or the most important, or of the suite of attributes, you're not going to meet precision requirements for the limiting attribute, which is the one that's most variable. So anyway, in this example, we have 9 candidate strata that you can edit the spreadsheet appropriately to reflect the appropriate number of strata, or you could have some large number of strata, like 20 strata, and then only fill in the first few. You could make a more advanced spreadsheet using these same principles. What I've done here is I've made it so you enter the CVs that you calculated elsewhere. You could enter the standard deviations, because what I did is, for the example I created the spreadsheet for, all we had was the stratum weight, the CV, and the mean. I didn't have the standard deviations, which I need for my below calculations. So I back calculated them. to back calculate them, you just multiply the mean by the coefficient of variation to get the standard deviation. It's a simple calculation. But you could manually enter these in yourself. So here we've calculated the global mean, which is just the weighted average. Here we calculate the global coefficient of variation. We do that by calculating the weighted variance, taking the square root of the weighted variance, this portion of the spreadsheet, and dividing it by the weighted mean. Here we assign the confidence level for our allowable error, 95% confidence interval we're interested in, and this precision goal. And the question is, what percent of the estimate do we want the confidence interval to be? So what is the sampling error percent that we're shooting for here? Here I want, by choosing these two parameters, what I'm in effect saying is that I want the inventory that I designed to achieve 10% sampling error at the 95% level. That's what entering these two data implies. So we have two options here, depending upon what your goals are, either Niemann allocation or proportional allocation, proportional to the area. In the proportional case, we don't make any effort to optimize. This is the equation for the Niemann allocation. It basically it puts more plots in areas with more variability based on the standard deviation of the strata from our pre-survey. So in this example, we would need, and again, these are just random numbers. We would need 62 plots for proportional allocation, and we would need only 40 if we were to ultimately do Niemann allocation. So you have to decide how you're going to allocate the plots before you choose which required sample size to proceed with below. So in this section, we take these 62 required plots in order to achieve 10% sampling error at the 95% level, and we assign them proportionally across the strata, proportional to the areas. And again, we use, for these, as you can see, we're using the stratum weights, which are the weights derived at the area proportions. Here in Niemann allocation, we're implementing this equation to determine for each stratum how many plots we would need to assign them optimally with the optimality criterion being the standard deviation of the stratum, the variability of the strata, in other words. So you can see that those 62 plots, we've assigned them across the strata, and we summed 62 as expected. Same thing with the Niemann allocation. We summed it to 40. So this is just sort of another way of looking at this. I didn't want to put everything in one spreadsheet to make it complicated. This is the exact same spreadsheet. The only difference is here I put in the variance of the mean for each stratum, and I've done the same here. So when we take the square root of the weighted variances of the mean, we get a standard error. And in order to calculate, this is sort of like a weighted standard error. And then in order to calculate the global sampling error, which we would achieve, we just take the global standard error, and I'm putting it times 2 here in my example. And again, you could tweak this to make it more accurate. It really should be the t-value associated with the confidence level and the number of plots. I'm just saying 1.96 is basically 2 in this case, if you get the idea. When I say 1.96, that's the t-value associated with a large number of plots and 95% confidence level. So you can you could change that 2 to using the t inverse equation if you wanted to. The point of doing it is just to check to make sure that, yeah, I get around 10% sampling error in both cases, which is what I had asked for originally. So it's just sort of a double check, and it also shows the user what's really going on here. We're pretending that these were the real data that we collected for our inventory. Anyway, that's all. I'll put this spreadsheet in the comments associated with this, or the information associated with this video.